So a round of applause, please, for Fabio and Till.
Thank you. OK, thanks, everybody. Let's get started. Let's see. OK, yeah, great. So I want to set a little bit the stage before we dig deep into the implementation details and what we did. And so I want to start with analyzing like a really simple machine learning workflow, where you basically have a bunch of data, static CSV files, for instance, and you read them up, you train a model, and then you make prediction, and that's it, kind of it, right? And that's fine, but that's usually not the end goal. The end goal is to build what we call a machine learning system, right? The difference between just a model and a machine learning system is that a machine learning system, you get on one side, data continuously getting updated. You may have streaming data coming in, but even daily batches or hourly batches. And on the other side, you have you continuously have to make predictions, right? Again, either in real time or in batches every now and then. Now, if you look at this one, you have a couple of challenges that you need to sort out if you want to implement a machine learning system, right? The first aspect is to take care of updates coming in of the data, right? You have to consider either appending new data, updating existing data, handling data coming in at different rates from different systems, and much more, right? The second thing you want to do is you want to look at retraining your model every now and then, depending on the use case. Data outside changes. Your model needs to adapt to new data. So you have to have a situation where you keep retraining your data every now and then. And the last part is that now you have a bunch of new contexts that you can use to make better predictions. So you need to provide the same context that you use for training your model. You need to do that when you make predictions as well. So the way we solve this problem is in two ways, right? So the first part is we break down what we have as a kind of monolithic pipeline into 3 different stages. There you go. The first stage would be a feature pipeline, which is just takes up some raw data, computes features, and write them somewhere. The second stage would be a training pipeline, which is basically just training your model, retrieving the features, training your model, either in scikit-learn model, PyTorch, whatever it is. And the last part of the pipeline, that last step would be an inference pipeline, which is basically saying, I'm going to make predictions either in real time or in batches. This is the first step of solving the problem. The second problem that we have is that if you look at this one, we need a way for all the 3 pipelines to communicate with each other, right? We need a place to store the state, and that's the feature store. So that's where kind of OpsWorks comes in. The idea behind OpsWorks is provides a place where you can actually store features and retrieve them for both training your model and also for doing inference, both real time and batch. And OpsWorks extracts a bunch of metadata, so you can keep things consistent throughout all the stages, all the different pipelines. Now, under the hood, how OpsWorks is implemented has 2 essentially storages, and a metadata layer in between. The metadata layer tracks and builds up the UI. We have a booth, so you can come later and see the UI and see what you can do. But the other 2 aspects are the offline data storage and the online data storage, right? The offline data storage is what powers all the model training and all the batch predictions. The online data storage is what powers the real-time inference, essentially. The online storage is a real-time in-memory database. It's fast. In today's talk, we're going to be focusing only on the offline part and how we improved it and why we did that. So the reason we wanted to look at performance of the offline part is that if you look at OpsWorks is not the only feature store out there. There are a bunch of other feature stores out there. And if you look at how they are implemented under the hood, there are 2 technologies that really shine. One is either built on Spark, or they are built on data warehouse, either cloud or on-prem. The problem with both technologies is that they are quite slow. If you think specifically Spark, it takes 30 seconds just to start the application, and then get another little bit of time to schedule the executor, and it's a minute has passed, and you have done no work at all. So if we compare this one with the initial workflow where you have static CSV file, train a model, and off you go, it's much slower, right? So it provides like a really worse kind of user experience for Python developer and data scientists. So we want to improve that. The way the feature store works essentially is that Spark was used for essentially joining different features together and passing them to either the training pipeline or the inference pipeline using the JDBC protocol. JDBC is another source for performance issues, and Till is going to dig in details on why. But essentially, at the high level, what we did is we replaced Spark with DuckDB. And the other thing we did was we replaced JDBC with ArrowFlight, the ArrowFlight protocol. This makes things a little bit like way more faster, not a little bit. And so now Till is going to go into details on the implementation details and explain how we did it.
All right. Yeah, first I want to talk about Apache Arrow. So Apache Arrow is an in-memory data format, and it has a columnar data layout in memory. So that makes it very optimized for analytical workloads because data in the same column is close to each other in memory. So another feature of Arrow is that you can do zero-copy reads. That means you can, instead of loading the data from pandas to a certain file and then read it back from with DuckDB, you can just write a query in DuckDB that reads pandas data directly from memory without any copying. So what the Arrow framework itself, or the Arrow package also features, is a client-server framework. So you can build Arrow-based data services with this framework. And you can do, for example, something like you have a backend service. There are some Arrow tables that can come from Parquet files or from wherever. And you can send them through the ArrowFlight RPC protocol to your client that is very lightweight and lives in a Python process, for example, in a Jupyter Notebook. And the great thing about it is that it's much faster than other database network protocols like JDBC. This is a benchmark, for example. So if you want to transfer 16 million rows from your server to your client, and if you use ODBC, that takes 70 seconds. If you use ArrowFlight for this, this only takes like a couple of seconds. And one of the reasons is that the ArrowFlight protocol doesn't break with the columnar data orientation of Arrow. So this adds a lot of overhead if you have a row-wise protocol like JDBC, and that's alleviated when you use ArrowFlight. Yeah, so what is DuckDB? DuckDB is an analytical database management system, so it's built to answer analytical queries to your data. It's lightweight and it can run in process, so that means DuckDB can run in your Jupyter Notebook, it can run as part of your ETL script, or it can also run in your ArrowFlight server. Yeah, and it's super fast. So when you look at the benchmarks, on this particular benchmark, you're doing joins between tables of 100 million rows, 5 different queries, and DuckDB can process them in 20 seconds, and Spark takes 20 times as much to answer the same query. What it also features, it features larger than memory data processing. So if your data set doesn't fit into memory, that's not a problem for DuckDB. It can offload intermediate results to disk. And so it supports also various data formats, storage connectors. It's very versatile in that sense and has lots of useful SQL extensions. For example, the as-off join that we extensively use in the feature store. Yeah, and of course it also has the zero-copy integration with Arrow, and that's not only for reading, but you can also materialize the query results right into an Arrow table. So in this example, you create an in-memory instance of DuckDB, and then you read a Parquet file, or you run a query on the Parquet file. So, and the query result you will get back as an Arrow table. So, yeah. I'm going to talk about how this was all useful to basically implement our DuckDB ArrowFlight powered feature store. Yeah, the feature store is using hopsfs, which is a file system that was developed by Hopsworks. It's a distributed file system, and it's based on HDFS. And the feature groups, so the different tables that contain features, are all stored in Hoodie tables, in the Hoodie lakehouse format on this distributed file system. And training data sets, so that combine different features, can also be stored on the same, on the hopsfs file system. Usually we would have the Spark job running that joins tables, and then it either sends them directly back to to a client in the Jupyter notebook through JDBC, and there's a SQL Alchemy client in the Jupyter notebook and a Python process, or it materializes the result directly to disk, so others can consume it from there. And the idea is to basically replace this part with DuckDB and ArrowFlight. There are a couple of challenges that we faced, or where we thought, okay, will this work out? One of them is we need authenticated authorized access to the server backend. Every client has to authenticate itself. What is really nice is that ArrowFlight also comes with MTLS, so everything is encrypted and also authorized. The second thing is we need to read from our hopsfs file system with DuckDB. And that works actually surprisingly simple, because there is this Python package called fsspec, which is a file system interface for Python, and DuckDB is compatible with that. So by only adding 3 lines of code, we can make DuckDB read from HDFS directly. So we have that challenge solved. Now the next thing is, on this hopsfs file system, there are these Hoodie tables, and they're basically Parquet files that are partitioned into different folders, partitioned based on a partition key that the user defines, and it also keeps track of the data changes over time, so it's versioning the Parquet files when someone updates data in there. It's a copy on write mechanism. So we had to write some logic to identify which of those Parquet files are representing the latest snapshot version of the table in there. We did that with a combination of Hoodie metadata and file names. There's more in the blog post. There will also be a QR code of the blog post later on. I don't want to go into too much detail on that. But we get these files that represent these Parquet files that represent our tables, and we just register them as temporary tables in DuckDB. And what you can do then, you can just run your query. We can run the query that constructs the training data set on these temporary tables. In this example, we are joining a user table or user features with other features. And we filter this to only users that live in the Netherlands. And in the ideal case, the data would be partitioned by country. And so what we do then, when we identify the relevant path in Hoodie, we basically push the filter to the file system level and only register those Parquet files that are actually relevant for the filter that we have in the query in DuckDB. So, yeah, and we use as-of joins, which are a really relevant feature for us, because we always want to make sure that the features, the user features we are now joining, the other features we are joining onto the user features, that they're not leaking information from the future into our training data set. And that's an inequality join, or an equality join on the IDs, but an inequality join on a timestamp, and that's something that is very difficult for databases to do efficiently, because if systems don't optimize for that, you will end up with a cross product in memory, and that will explode. So, but this as-of join feature exactly optimizes for this case. Yeah, the last part, how do we make this stable, right? This is a system that should run in production, has multiple users that come with different queries. We cannot really anticipate how large the queries are, how large the data sets are, so on. So what is necessary then in DuckDB to use this out-of-core feature, so offloading compute intermediates to disk, is that you specify a memory limit and also specify a temporary directory. So, and this is all that DuckDB needs to be able to process larger than memory data. Second thing is, because these joins are quite large, or the tables can be large, and we want to not stress the server too much with getting multiple requests, with basically DuckDB having to run multiple queries at the same time. So we have one server instance that can run one query at a time. We queue the other requests. Because we don't want the other clients to be waiting, we just replicate the ArrowFlight server instances and load balance between them. And with this, I hand over back.
OK, thanks. So after doing all this work, we wanted to check how fast this thing was and how we compare with other tools out there. Right, so the first thing we did was to set up a benchmark using the NYC taxi dataset. And we did a little bit of a different benchmark than usual. Like as Till was explaining, when you are joining multiple features from different feature pipelines for creating a training dataset, you don't just do a normal join. You end up doing what's called a point-in-time join, right? What essentially that means is that you see the red dot is our prediction target, is our label, is the time for which the label is valid. We want to join the label with, let's say, feature A and B, but as there are multiple updates, because data is coming in continuously, we want to make sure we pick the values of those features that were valid at the moment the prediction target was there, right? So this creates a little bit of a complex join. If you're expressing it in Spark, if you're expressing it in DuckDB, there is a nice operator to abstract away that complexity. But essentially, we run two different benchmarks, right? The first benchmark is basically retrieving all the data into a Pandas data frame in the client. We compare a bunch of other tools out there over different dataset sizes, from 5 million all the way up to 50 million rows. And you can see we are between like 7 and 45 times faster for the 10 million rows. And if you're using pure Spark, you won't be able to achieve the 20 million, and you won't be able to finish the 50 million either, essentially, right? So that's why you don't see any red lines there. The last part is, as Steve was explaining, ops is an option to materialize all the data set into either Parquet files or CSV files. So we run a benchmark also on that one. Here, Spark managed to succeed for the 20 million rows, but it failed again at 50 million rows. And again, the DuckDB solution is significantly faster than other solutions out there based on either Spark or a data warehouse. So to conclude everything, this new service kind of brings a Python interactive user experience to the feature store. So people that were data scientists that were used to have a local workflow, reading and training models directly on the local Pandas data frame, they can replicate that experience using a feature store. Significantly better performance than other solutions out there. Spark, though, is still an option. If you have several terabytes data sets that you want to join together, you can still fall back to using a Spark workflow. You will have to allocate enough resources to get it running, but the option is still there. That being said, if you want to have a more in-depth version of this talk, like we wrote a blog post as well, you can scan the link here. I think there is a channel on the PyData Slack where we're going to post a slide as well. So you can go through in details about the actual implementation as well, and a little bit more in terms of benchmarks and so on. I have to say, if you're interested in working on these type of problems, we are writing. If you find me and there is another colleague of mine, we have a booth there. It's the greenest thing you could find in the entire location, so you cannot not see us. Please come talk to us, and we'll sort something out. The other thing I want to mention, if you're interested in the feature store space and so on, we are organizing a conference. It's online. It's on the 11th of October. There are a bunch of speakers, us being one of them, but a bunch of other companies are presenting their solution and their setup. It's free, so you can just register. And that's about it. Yeah, if you're interested in talking more, I guess we have time for questions. Or again, we have a booth out there, and so you can come talk to us during the event afterwards.
Thank you so much, Fabio and Till. Big round of applause.